Alright, we'll make a start. Alright, so, oops, can't spell. So finding equations. Book calls it families. People freak out when we use the word families, so we won't use the word families. So consider the functions with the rules of the form fx. Oh, sorry, I didn't write that in the board, did I? So this is from the text. I'm going to do just one question from the text. Page 457. And 56 example. 32. So consider the functions of the form fx equals x minus a squared and x minus b. Where a and b are positive constants, so a and b positive. And the other requirement is that B is greater than A. Alright, so we may or may not need to use those later. Alright, so find the derivative of, where are we? Find the derivative of fx with respect to x. So part A, we want to know what f dash x is. Now, we haven't actually done this using the calculator yet, but I will do this during the calculator, because last year on the exam there was questions that you had to use your calculator for to do this stuff, because they had some quite complicated functions. So in exam 2 last year, there was a bit of that. So just make sure that you know where to find all of that. So, skip all this stuff. Right. Come on. Doesn't want to play the game, or does it not want to play the game? It's green. There you go, somewhere got the wrong thing. All right, so in our calculators, in the keyboard, in Math 2. Alright, so in keyboard Math 2, in the third line down, here the third line down, this one's clearer, there's our calculus stuff, and so derivative is this one here. So using that template, and we are going to differentiate our function x minus a squared x times x minus b, and it asks with respect to x. So whatever it asks with respect to, we put down there. So with respect to x, and then inside the bracket we put the function. So the function is a bracket, and it's x minus a, so we just go to the A, B, C's and use a. Where are we? It's a QWERTY keyboard. There's a. Oops, wrong one. Close the bracket, squared, and then the next bracket is x minus b. There's b. And we close that bracket, and then exe, and there it is. So that's differentiated it for us. So on our calculator, the calculator says 3x squared plus a squared minus 4ax minus 2bx plus 2ab, what the calculator says. All right. So it's not overly handy, it's a little bit messy. So we're going to try and neaten it up. So we're using the D whatever. So if we want to then neaten it up, we can then ask it to transform it, in other words, factor it. So if we then go to action transformation factor and say, like, can you do something with that for me? And then it might put it in a form that is a bit nicer. So if you then go action transform factor, then you get that the derivative is x minus a bracket 3x minus a minus 2b. Alright, which is in a bit neater form than what the calculator gave us in the first place. Alright, so there's part A. Part B says find the coordinates of the stationary points. So what do we know about stationary points? Gradient 0, yep. So f dashed x equals 0. So this factorised form is going to be far more useful to us than this, because with the factorised form, when we make that equal to 0, what do we then use? Null factor law. Yeah. Alright, so using the null factor law, x minus a is 0, or 3x minus a minus 2b equals 0. So x is either a or add a and 2b and then divide by 3. We get that. So we've got two stationary points. It says find the coordinates of the stationary points. We've got two, so what do we now need to do with these?
Put them in the
Put them in this one. Good idea. Alright, so we need the y values as well. When I ask for the coordinates, we need the x and the y. So when x is equal to a, f of a would be a minus a squared, a minus b. And that one's going to be equal to 0, yep. And when x equals a plus 2b on 3, now getting a bit, let me get rid of that. Put that in. You get a plus 2b on 3 squared times a plus 2b on 3 minus b. And that's something we might want to do on the calculator. Where are we? Oh, go back. Or we can expand it, so I'll just expand it. So if I expand that, got a square top and bottom, squaring the top line there, I'll get a squared plus 4ab plus 4b squared over 9. And common denominator here, a plus 2b minus 3b. Which is then a minus b over 3. And then when what have I done?
Yeah, that's what I missed.
Where have I made my mistake?
What happened to the minus a in the first
Oh, in here.
one? Yeah.
Well, thanks for that. I forgot that, didn't I? Thank you. Let me go back. Rookie mistake. Oh. I wondered why it wasn't working out, because I wasn't doing it properly. Alright, so it's x minus a, this minus a here. Right. So a plus 2b on 3, and then a plus 2b on 3 minus b. Alright. So common denominators first of all. Let's do that first. That might work out a bit easier there, mightn't it? A plus 2b minus 3a over 3. A plus 2b minus 3b over 3. So this is now 2b minus 2a over 3. And this one is a minus b over 3. Right, let's do better. So, I said you might want to be doing that on the calculator. Alright, so if I just square our 9 there, now the other thing that I can do, multiply them over 27, a minus b. Alright, with this one here, what do we notice about that and that? They're both 2's. So I'm going to take a 2 out. And I'm also going to take a minus out. You might be thinking, why is he taking a minus out? Because if I take a minus out, what's going to happen here? A, that becomes A minus B, yeah? Squared. And so then I've got an A minus B here, yeah? And an A minus B here. Now the square bracket, I've just still haven't squared that yet, so I've just taken the minus 2 out as a common factor and still kept it inside here.
Is that 2 meant to be inside
Which 2?
that? No.
This one?
Yeah, no, I'm good now.
No. So all I've done is I've changed that to that.
Yeah.
So now I'm going to square it. And so when I square negative 2, I get 4 A minus B squared. And then I've got this A minus B as well, over 27. A minus B cubed over 27. All right, so you can see it's pretty messy. So you probably want to get your calculator to do that for you. And if you get your calculator to do that for you, it may not give it in that nice, neat answer. So if it doesn't, then just do what I did before with this one. Now get something that's not very neat and ask it to factor it to see whether you get something that's neater. All right. Now, I know on exam 2, with your calculator, I doubt that they would ask you to do that by hand, but you need to use the amount of space that you're given and the number of marks. So if you're only given a little bit of space, like that takes a lot of space, if you're only given a little bit of space and only a couple of marks, then you're not being expected to do it by hand. All right, so our 2 stationary points are at A and 0, and A plus 2B on 3, and this one. All right. Show, part C says, show that the stationary point at A0 is always a local maximum. All right. I've got that. I'll rub all this off. Leave that there. Alright, so part C says show that A0 is a local maximum. Alright. So in the start, our function f(x) was x minus a squared and x minus b. Now, what was the restrictions on A and B? What were they?
A and B have to be positive and B has to be bigger than
Right, so they've both got to be positive and B's got to be bigger than A. So the way we're going to show this is not, we're going to ask you to show, you've got a whole bunch of things that you could do. All right, with this, what I'm going to do is a sketch to show it. So if that's X, what do we know? We know A and B are both positive, so A and B have got to be up here. B has got to be bigger than A, so if A is here somewhere, B's got to be up there somewhere. there's one other thing about A and B. Anyone tell me what that one other thing about A and B is?
X minus A is a turning point.
Turning point? Yep.
B is an intercept.
B is an intercept. Right, so B is an intercept. A minus this X minus A is the turning point. But what's special about this particular turning point?
It's on the outside.
It's on the axis. So if A is here, then B is here somewhere. Yes, correct? So we've got a turning point or stationary at X equals A on the axis. We know that bit. We've got an intercept at X equals B. And what sort of graph is this? Cubic. So we've got a squared there and another X there, so it's a cubic. Now, is this cubic the normal one that starts at the left and finishes at the right, or the other way around? It's the normal one, yeah. So it also it's not got no negative in front of any of those X's. So it starts bottom left. So this particular one goes something like this thing, doesn't it? Now, this point here, what's that X? Well, just as that X there is our, what was it, A plus 2B over 3. So this turning point here, 2B over 3, and the so that point there, that's that other stationary point that we found. I know they didn't ask you to show that, but I'll open that anyway. Now remember, B is bigger than A, so this bit here is going to be negative, and when you cube a negative, you still get a negative. So it's going to be down there. Yes? All right, there's a fair bit in that, a little bit complicated. Anything clarified? Yes.
How do you know that the A isn't a minimum turning point and the maximum turning point is further to the left? Is it because is it because B is bigger than A?
Yes. Yes, because of this. If A is here, B has to be that way.
Yep.
And so that's why they've said that in the question at the top. That's why they've said that B's got to be greater than A. Otherwise you wouldn't, like you say, if B was not and B was down here, then yes, it could be different altogether. But the way the restrictions are, then it has to be like that. Anything else on that before? Yes.
Why is that the local maximum?
Right, why is it the local maximum?
So I thought,
A and B have to be positive, so they have to be up here. B has to be bigger than A, so if I've put A there, B has to be that way.
yeah, but why wouldn't, isn't the maximum the highest point on the graph?
No,
Local.
Local. So it's like, just what you can see,
In the area.
what's like the highest
So
point.
here,
Distance.
Yeah, but
in this area, in this locality,
yeah,
that's the highest point.
but if B just has to be bigger than A, couldn't you just move it over, like,
I could move it over there, but still, how big's the location? To make my location small. So I understand what you're saying, Ethan. I understand, I could make B right here,
but then,
and then it goes like this. and that's still the highest there.
That's not really what I meant, but.
It's not what you meant.
I'll talk to you
I'm
later
not-
about it, 'cause obviously I don't understand.
Then I'm not getting what you're asking then. Alright, so when it says local, it doesn't have to be the whole lot. Yeah, you're right, the maximums are here somewhere. But in, around this area here, around x equals a, that is the highest point. Alright, anything else with that? Anything about that thinking to get to this? No? Right. And then the last bit says, find the values of A and B if the stationary points occur when x equals 3 and x equals 4.
It's going to take up a lot of room, so my pages get pretty full.
This is going to take up,
How good?
this is going to take up some, not very much room.
Sweet.
Stationary points, so that's
Only like.
It's not going to take much room at all. Whether you've got enough on your page or not. So we know we've got stationary points when x equals 3 and x equals 4. So what does that mean? So
that
looking at
means
this,
that at the points, at the turning points, x equals
yep, so
3.
turning points, x equals 3,
x equals
x equals 4, correct. So, at this one here, if x equals 3 and that turning point is at x equals a, what does that mean about the value of a?
A equals 3.
Yeah. So it's x equals 3 and it's also at x equals a, so from that we can say that a is equal to 3. So now if we know that a equals 3, and we also know that there's another turning point at x equals 4, and that other turning point at x equals 4 relates to that there, doesn't it? Alright, so 4 then will equal to, and we found out a is 3, so 3 plus 2b over 3. Rearrange that. 12 equals 3 plus 2b. Take 3, 9 equals 2b, so b is 9 over 2. Alright, so there's other ways of getting to that as well, but it's as good as any. Right, any questions on that?
So if we substituted x equals 3 into the first equation,
Yeah, because we know there's a stationary point at x equals 3, there it is.
so we just get...
And we already found previously when that there was a turning point, stationary point at x equals a, which is this one here. So x equals 3 and x equals a, well, a's got to be 3. And then once we found a is 3, then the other stationary point, turning point, is got to be at the x equals 4. And we found a is 3 over here. Right. So there's other ways of doing it, but in this case, that one's probably as easier. Yep.
Can you explain how you got a equals 3 again?
Right. So here, we've found that there's a turning point at x equals a. And then when we've looked at our graph, that's it there, there's our turning point.
Yeah.
And because we've got x equals 3 and x equals 4 here, and we know that our a is bigger than b, so if one of our stationary points, which in this case, they're both turning points. And if one of our stationary points is x equals 3, it's got to be the one on the left, doesn't it? Because x equals 4, it's to the left. So the left of these stationary points is this one here, isn't it? Which is at x equals a, which we're then told is at x equals 3, this left-hand one. So seeing as the x value here is just simply a, then a and 3 are going to be the same.
Is that all?
Yep, that's it. So, any other things needing clarifying? Yes, Steve.
Yeah, come in so I can.
Yep, I'll come here. All right. All right, so this is the last bit of this. This is 10G. Let's start integration on Monday.